Giant exoplanets exhibit a higher heavy element content compared to solar system giants, which cannot be fully explained by existing theories such as collisions between planets, accretion of volatile gas, and accretion of gas enriched in micrometre-sized solids. This study proposes a combined model that incorporates gas accretion enhanced with vapor and small micrometre-sized dust grains. The model involves inward drifting and evaporating pebbles, which influence the dust-to-gas ratio and heavy element content of the disk. As pebbles drift inward, the volatile component evaporates, enriching the disk, while the smaller silicate core continues to move inward, leading to a pileup of material inside the water ice line, increasing the dust-to-gas ratio in this region. Gas-accreting giants can accrete large fractions of small solids in addition to volatile vapor, under the assumption that these small dust grains follow the motion of the gas even through pressure bumps generated by gaps between planets. The effectiveness of solid enrichment requires a large disk radius to maintain the pebble flux for a long time and a high viscosity that reduces the size and inward drift of small dust grains. However, this process depends crucially on the debated size difference of pebbles inside and outside the water ice line. The volatile component released by inward drifting pebbles can lead to high enrichment with heavy element vapor, independently of a size difference of pebbles inside and outside the water ice line. The model emphasizes the importance of the disk's radius and viscosity to the enrichment of dust and vapor. By combining estimates of dust and vapor enrichment, the model can explain the heavy element content of the majority of giant planets. The study highlights the significance of considering atmospheric abundances and total heavy element content of giant planets as additional constraints on planet formation theories. Interior models can estimate the heavy element content of gas giants, and observations suggest that hot Jupiters have surprisingly high heavy element content, nearly twice as much as Jupiter. Alternative theories, including planetesimal accretion and mergers between gas giants, have been proposed to explain this phenomenon. However, these theories have limitations, and the pebble drift and evaporation scenario, supported by disk observations, provides a natural explanation for the heavy element content of most massive giant planets. This research paper delves into the enrichment of dust grains in the inner disk region, attributed to differences in pebble sizes inside and outside the water ice line. Utilizing a 1D viscous disk evolution model that incorporates pebble growth and drift, evaporation, and recondensation of pebbles at evaporation fronts, the authors calculate the heavy element content of giant planets by summing the vapor component and the small dust component. The study underscores the importance of various disk parameters on the heavy element content in disks and the growth of single giant planets. It reveals that high dust-to-gas ratios in the inner disk region can be achieved over a long period, which could significantly enhance the local dust-to-gas ratio. The enrichment of small dust grains in the inner disk is attributed to the different pebble sizes inside and outside the water ice line, leading to a traffic jam that enhances the dust-to-gas ratio in the inner disk. The composition of giant planets is influenced by the dust-to-gas ratio originating from small dust grains that follow the motion of the gas. The paper also discusses the impact of outer giant planets on the composition of the inner disk, including blocking pebbles and taking away a significant fraction of the available gas, leading to a different planetary growth pathway. The study emphasizes the need for more detailed calculations to fully understand the heavy element content of giant planets. The research presented here focuses on the enrichment of inner disks and giant planets with heavy elements, using a two-dimensional model of a protoplanetary disk. It highlights the importance of pebble transport and evaporation fronts in the distribution of dust and gas within the disk. Simulations show that the dust-to-gas ratio in the inner disk initially increases due to the pileup of inward drifting pebbles at evaporation fronts, particularly for disks with smaller radii and higher viscosities. However, as time progresses, the dust-to-gas ratio decreases significantly and reaches subsolar values towards the end of the disk's lifetime. This decrease is more pronounced in smaller disks, which aligns with analytical estimates. The heavy element content of the gas phase, sigma heavy, increases significantly inside the evaporation fronts, leading to supersolar values throughout the inner disk region. This enrichment lasts for the entire lifetime of the disk and is influenced by the disk radius and viscosity. The duration of vapor enrichment depends on the disk radius and viscosity, with larger disks maintaining their vapor enrichment for a longer time due to a longer pebble flux. The reduction in vapor enrichment is slower compared to the dust-to-gas ratio, as vapor follows the evolution of the gas, while small dust grains are influenced by inward drift and pebble transport. These findings provide insights into the role of pebble transport and evaporation fronts in shaping the composition of inner disks and giant planets, suggesting that the enrichment of heavy elements in these regions may be more complex and dynamic than previously thought. In their research, the authors delve into the enrichment of heavy elements in the inner regions of protoplanetary disks, focusing on the interplay between dust and gas. They discover that the time-integrated dust-to-gas ratio and heavy element content at 0.5 astronomical units are influenced by the disk's viscosity. At low viscosities, the initial enrichment by solids is greater due to faster inward drift, whereas at high viscosities, the picture reverses, and the time-integrated dust-to-gas ratio is higher than the heavy element content in the vapor phase. The time-integrated dust-to-gas ratio and heavy element content at 0.5 astronomical units are depicted in Figure 3, illustrating how the heavy element content of a putative planet that accretes with a constant rate would evolve. The results suggest that the heavy element content in the gas phase is higher than the dust-to-gas ratio in the inner regions of the disk, especially at the end of the disk's lifetime at 3 mir. The authors also explore the implications for planetary formation, estimating the maximum heavy element content that a gas accreting planet could have. Following the approach outlined in Morbidelli et al., 2023, they assume that small dust grains can be successfully accreted with the gas flow onto a growing giant planet in the inner disk. The results, shown in Figure 4, indicate that the planet can accrete gas with a heavy element enrichment of around 30.5%, which explains the majority of the data from Thorngren et al., 2016. However, the authors note that the final heavy element content of a growing planet is set by the disk parameters, and only a combination of vapor and dust accretion can explain the constraints derived from observations. They also discuss the limitations and implications of their work, including the importance of disk parameters and the potential for planetesimal bombardment. This research paper delves into the enrichment of inner disks and giant planets with heavy elements in protoplanetary disks, focusing on the evolution of heavy element content in both the solid and gas phases over time. Utilizing a combination of pebble drift, planetesimal formation, and chemical evaporation models, the study reveals that the enrichment of heavy elements in the gas phase is primarily driven by the inward drift of pebbles and their subsequent evaporation, leading to an increase in the heavy element content of the gas phase. This enrichment is more pronounced in disks with larger radii and higher levels of turbulence, as represented by the parameter alpha. The paper underscores the importance of understanding the fragmentation velocity, which affects the size distribution of particles in the disk. Laboratory experiments suggest a transition in fragmentation velocity at around 12 astronomical units, although recent observations have cast doubt on this theory. The formation of planetesimals also plays a crucial role in the enrichment process, as they consume pebbles and reduce the pebble flux, ultimately impacting the enrichment of the disk with small dust grains or vapor. The study's findings are presented through various figures, including Figure 2, which illustrates the time evolution of heavy element content in the gas phase for different disk radii and turbulence levels. Figure 3 shows the time evolution integration of heavy element content at 0.5 astronomical units, either from the solids or vapor, for disks with specific radii and alpha values. These figures demonstrate the significant enrichment of heavy elements in the gas phase over time, particularly in disks with larger radii and higher turbulence. In conclusion, this research provides new insights into the enrichment of inner disks and giant planets with heavy elements, emphasizing the key role of pebble drift, planetesimal formation, and chemical evaporation. The findings have implications for our understanding of planetary formation and the composition of giant planets, suggesting that these bodies may be more enriched with heavy elements than previously thought. This research paper delves into the enrichment of giant planets with heavy elements, emphasizing the role of dust and vapor in their formation. The authors propose a pathway for this enrichment, which is dependent on disk parameters such as disk radius, viscosity, and the transition in fragmentation velocity at the water ice line. They find that high enrichments of planets with vapor are possible for large disk radii and low viscosities, independently of a transition in fragmentation velocity. Conversely, a high enrichment with dust grains requires a large disk radius, high viscosity, and a transition in fragmentation velocity at the water ice line, which remains a topic of debate. The study also underscores the importance of considering the overall composition of materials in the disk, as variations in the stellar C/O ratio and metallicity can influence the amount of vapor enrichment and the availability of refractory materials. This suggests that the origin of the heavy element content of giant planets should be re-examined on an individual basis rather than just with the iron component. The authors acknowledge the limitations of their model, including the assumption of smooth disks and the lack of consideration for the effects of small dust grains and vapor enrichment on the heavy element content of growing giants. They note that future simulations need to investigate these issues in detail. Furthermore, the paper mentions that the ratios of the vapor component to the Dustogas ratio could be used to estimate the volatile to refractory ratio of planetary atmospheres, a potential tracer of planet formation histories. Enrichment of inner disks and giant planets with heavy elements is a crucial process in planetary formation, and dust plays a pivotal role in this mechanism. Understanding the delivery of heavy elements to these celestial bodies is essential, as they are necessary for the formation of terrestrial planets and the potential for life in exoplanetary systems. Current research highlights the importance of pebble accretion in the growth of giant planets, where Dustogas ratios significantly impact the efficiency of this process. The subsequent enrichment of heavy elements in the inner disk is directly influenced by these ratios. Additionally, planetesimal formation, facilitated by the streaming instability, is a critical step in this process. The study examines the effects of varying disk models on the enrichment process, including the impact of different Dustogas ratios and the presence of multiple giant planets. The findings have significant implications for our understanding of planetary formation and the potential for life in exoplanetary systems. Further research is necessary to elucidate the complex interplay between dust, gas, and planetesimals in the formation of inner disks and giant planets. This study underscores the need for continued exploration into the intricate mechanisms governing the enrichment of heavy elements in these celestial bodies, ultimately shedding light on the origins of life in the universe. In this appendix, we provide additional details on the model parameters and simulations used in the paper. Table 8.1 presents the condensation temperatures and volume mixing ratios of various chemical species, distinguishing between volatiles and refractories based on their evaporation temperatures. The model assumes a fixed initial mass of 0.1 solar masses and an analytical viscous disk solution, resulting in a surface density gradient of approximately 1.08. The gas surface density evolves via viscous evolution equations with an alpha viscosity prescription, and the disk's temperature is determined by the equilibrium between viscous and stellar heating with radiative cooling. Using solar elemental abundances, the Dustogas ratio is calculated by summing over the mass fractions of the major elements, resulting in a Dustogas ratio of 1.47%. The code calculates the growth and drift of pebbles as a function of time, with the time evolution of the Stokes number of the pebbles shown in Figure 8.1. Initially, the Stokes number increases radially due to the decreasing gas surface density, but drops at larger distances after 0.1 m due to long growth timescales in the outer disk regions. High metallicity has significant implications on the Dustogas ratio and heavy element content in the gas phase. For disks with a metallicity of 3%, the higher metallicity allows greater enrichment in the Dustogas ratio and heavy element content, but does not prolong the duration of the pebble flux. Notably, the integrated heavy element content of the gas phase stays above 40% during the whole lifetime of the disk, while the Dustogas ratio drops below 10%. The impact of constant fragmentation velocities on the enrichment of inner disks and giant planets with heavy elements is explored through two sets of simulations, each with a different fragmentation velocity: 1 meter per second and 10 meters per second. The results show that constant fragmentation velocities lead to lower Dustogas ratios in inner disk regions, compared to simulations with a transition in fragmentation velocity at the water ice line. This limitation is due to the traffic jam effect, where particles inside the ice line have smaller sizes, restricting the dust-to-gas ratio enrichment in the inner disk region. In contrast, the heavy element content in the gas phase exhibits a different pattern. Inward drifting pebbles that evaporate at the evaporation fronts drive the enrichment of the gas phase with heavy elements. Since pebble sizes are identical in both simulation sets, the heavy element enrichment in the gas phase is independent of a transition in fragmentation velocity at the water ice line. The authors highlight the critical role of low disk viscosities in achieving sufficient enrichment of the gas phase with heavy elements. High viscosities result in rapid vapor transport away from the inner disk, leading to low enrichment. This underscores the significance of disk properties in shaping the formation and composition of giant planets. The analysis of the time evolution of dust-to-gas ratio and heavy element content in gas disks with varying parameters is presented. Figures B1 and B.2 demonstrate this evolution over a period of 0 to 3 mir. Figure B.1 illustrates the time evolution of the dust-to-gas ratio and heavy element content for disks with a high metallicity of 3% and a radius of RC equals 250 astronomical units, showing an increase in the dust-to-gas ratio and a decrease in the heavy element content over time. Figure B.2 displays the time evolution integration of the heavy element content of the gas phase at 0.5 astronomical units for disks with alpha equals 10⁻⁴ and alpha equals 10⁻3, highlighting the difference in the heavy element content's time evolution depending on the value of alpha. The findings suggest that high metallicity and varying alpha significantly impact the disk's composition and evolution, particularly the dust-to-gas ratio and heavy element content. These results are crucial for understanding the formation and development of planets and the potential for life to emerge on such planets. The paper's methodology, utilizing simulations with different parameters, provides valuable insights into the complex interplay between gas, dust, and heavy elements in protoplanetary disks. In the formation of giant planets and inner disks, the enrichment of heavy elements plays a crucial role. To investigate this process, simulations were conducted to model the time evolution of dust-to-gas ratios and heavy element content in protoplanetary disks. The fragmentation velocity of pebbles was varied, and its impact on the enrichment process was examined in disks with different radii and gas densities. The results reveal that the fragmentation velocity significantly affects the distribution of heavy elements, ultimately influencing the final composition of planets. For instance, higher fragmentation velocities lead to more efficient radial transport of heavy elements, resulting in their increased concentration in the inner disk regions. Conversely, lower velocities result in a more uniform distribution of heavy elements throughout the disk. The simulations also demonstrate that disk radius and gas density are critical parameters in shaping the enrichment process. Larger disks with lower gas densities exhibit more pronounced radial gradients in heavy element content, whereas smaller disks with higher gas densities display more uniform distributions. These findings have significant implications for our understanding of planetary formation and evolution. The results underscore the importance of considering the interplay between fragmentation velocity, disk radius, and gas density in determining the final composition of giant planets and inner disks. This research builds upon previous discussions on the critical role of these factors in shaping planetary formation and evolution, providing new insights into the complex processes governing the enrichment of heavy elements in protoplanetary disks.